Hello, this is lecture 4 from the College Algebra OpenStax book, using it as a guide. We are in the first chapter in section 1.3. It'll be radicals and rational exponents. Lecture 3, we did all of the laws of exponents. So if you don't feel like you're comfortable when we talk about rational exponents because you don't remember some of the rules, check out lecture 3, which is just about exponents. And that will be helpful for you to go back. So I'm going to assume that you know basic laws of exponentiation, exponents. And I won't go over that ground too much again. So we're going to start with the notion of a radical. I don't know where the term radical comes from. I didn't look it up. But it's a root. And we'll first talk about square roots. And the symbol, this, which I don't always draw very well, this is called the radical. The number underneath is called a radicand. And the whole thing is just a radical expression. Now, when you see the symbol without a number there, it's assumed to be 2. So just the radical without number, we're assuming square root. So if we have the square root of 25, now most of you might be familiar with, is 5. Why is this? You always want to know why in math. Why is this true? Why does this rule say that the square root of 25 is 5? So what a root essentially does, it wants to know 2 numbers that multiply that give me the radicand. It wants to know if I can evaluate the radical, I need 2 numbers that multiply that give me 25 that are the same number. If that's true, I can evaluate it. You can evaluate any radical. You'll get a decimal, stream of decimals. In most cases, it'll be ugly, so we like to simplify by keeping the radical so it's a little bit cleaner. But the gist is this. 5, I'm going to break down into its prime factorization. The nature of integers says that they can always be written uniquely as a product of primes. So 25 is 5 times 5. 5 is prime, so I can't break it up any further. That's the nature of primes. So 25 is the same as 5 times 5. The rule says if I have 2 numbers multiplied together, in this case I need 2 of them, right? Because it's a square root, that I can evaluate it by taking 1 of them out. And we'll get to higher roots later in this video. So let's look at some goofy stuff. What's the square root of 81? So let's look at the square root of 81. It's 9 times 9 is 81. So I know I can write the square root of 81 as 9. And 9 is 3 times 3. So 2 numbers that multiply to give me 9 is 3. So this evaluates to 3. Another quick example is we can do arithmetic with roots, just like we can any real number. These are real numbers, so we can add, subtract, multiply, and divide them. There'll be some rules we'll see later what we can do and when. Now, the square root of 36, if I want to look at a factorization, it's 6 times 6. Well, I just need 2 numbers. But if I needed to break this further, it'd be 2 times 3, 2 times 3. I can bring out a 2, I can bring out a 3. But all we really need is two numbers that multiply to give me 36. That's 6. Same with 25. It's 5 and 5. So that's minus 5. So it's 1. Okay. You become pretty quick at square roots when you recognize something about them. Let's look at the squares of the first 10 integers, positive. I don't know why I skipped 6, but let's go back. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, 36, 49, 64, 81, 100. All right, so the integers from 1 to 10 squared, the results are called perfect squares. So notice then that 1 is 1, 4 is 2, 9 is 3, 16 is 4, 25 is 5, 36 is 6, 49 is 7, 64 is 8, 81 is 9, and 100 is 10. Because when we take the square root of a perfect square, we get a perfect integer back. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the first 10 perfect squares. Once you know that, you can recognize the square roots a little bit quicker, and especially when you're simplifying them, reducing them, knowing this chart helps, right? All right, so let's get into some rules. In our previous lecture on exponents, we also had a product rule. The product rule says if I have the square roots of a times b, I can separate these into two separate square roots. I tend to hook the root radical symbol just so I don't have things, if I'm writing x times the square root of 4, that it's clear what's inside and outside. So sometimes I'll hook it because I can get sloppy. So product rule says if I have two things inside that are being multiplied, I can separate them into two separate radicals. An example, let's say 50x squared y to the third of z. So I can write this as square root of 50 times the square root of x squared times the square root of y thirds times the square root of z. All right, so that's rule number 1. We can reduce them this way. Now let's look at 50. Remember, if I can evaluate 50, I want to do so. So I know this is 2 times 25. And it's 5 times 5. So that's its prime factorization. 5 times 5 times 2 is square root of 50. So I can write the square root of 50 as 5 times 5 times 2. Since it's a square root, I want two numbers that multiply that give me 25 in this case. I can evaluate that. In other words, I can bring it out. 2 does not decompose that way. We can't have two numbers that multiply that give me 2 that are the same number because 2 is prime. So 50 becomes 5 square root of 2 x squared. This is an important property that the square root of a square is always just itself. And the reason is because the square root of x squared is the square root of x times x. And again, the rule says if it's a square root, I need two numbers to multiply that give me that number, in this case, x. So this is x. What about y to the third? So we have the square root of y to the third, means we have the square root of y times y times y. So again, I'm going to bring out a pair, which means I bring out a y, but I have the single y here, and I have to leave it inside because it doesn't have a pair. So we have 5 square root of 2 times x times y square root of y times square root of z. That's perfectly fine to leave it that way. It looks a little ugly to me. Remember, the product rule says I can combine the products inside. So I'm going to take what isn't inside and put out here 5xy. I'm going to take a square root, and I have 2yz. So this simplifies to this. All right, we have a product rule. We definitely have a quotient rule. And if you are watching this series, you'll know from a previous lecture that you guessed it, this is going to be a divided by b, take the square roots. It's the same as taking the square root of the numerator and square root of the denominator. No surprise. Let's look at an example. Square root of 7/64 is the same as square root of 7 divided by the square root of 64. Remember, if I can evaluate, I want to write the square root of 64 if I can as a number, square root of 7 too, but square root of 7 is ugly because 7 is prime, so we'll just write it like that. 8 times 8 is 64. It's one of our perfect squares, so this simplifies the square root of 7 divided by 8. Let's look at another example. We're going to have a lot of examples in this section. I don't think it helps just to write the rule. Having the rule and showing some examples helps to sort of stick in your head of why things are happening. We're going to write this as a numerator of 2a squared and the denominator of 9b to the 4th. The product rule says that we can write this as the square root of 2 times the square root of a squared divided by square root of 9. I don't know, that looks like an a to me. Sorry about that. 9 times the square root of b to the 4th. Now, the square root of anything squared is itself, so this is just a. Convention says we like to bring out the constants without roots in front of the radical. Just it's easier to see. And this will be b to the 4th times 3, but b to the 4th is the same as b times b times b times b. So for every 2, because it's a root, I bring out a b. So this is b squared. And that's it. A square root of 2 divided by 3 times b squared, which gives us the simplified version. So again, these are real numbers. So radicals, we should be able to add and subtract. And we'll start with the square roots. So the rule for adding and subtracting square roots is that the radicand, the thing under the radical, has to be the same. An example is if I have the square root of 5 plus 2 times the square root of 5, these are the same, the radicand are the same, so I can write this as the sum of the coefficients. So again, we have out here, we have 1 assumed, then it's 1 plus 2 is 3 square root of 5. It might not be that obvious. The why it's happening is, I don't want to get too far ahead of the course, but I could factor out these terms. They're like terms. So I can take out the square root of 5, and I'm left with a 1 here and a 2 here. And I get square root of 5 times 3, which is 3 square root of 5. So it's undistributing the square root of 5, so to speak. Factoring is undoing distribution. So another way to think about this is if I am adding these two things, the multiplication in front says I have 1 square root of 5, I have 2 square root of 5s. And if I add those, then I have 3 square root of 5. It's just another way to look at it. Another example maybe would be, let's use some variables. 2 square root of x minus 5 square root of x. Now the rule says if I have the same radicand and the same root, in this case square root, well, I'm just going to subtract the coefficients 2 and 5. So 2 minus 5 is negative 3 square root of x. Simple enough. Another example, the square root of 5 plus 6 times the square root of 20. Now notice that square root of 5 and square root of 20 aren't the same. Or are they? Well, let's see if we can reduce 20. Now 20 is 2 times 10, which is 2 times 5. So the prime factorization of 20, if I were to write 20, I can write it as 2 times 2 times 5. The square root says I need a pair that multiply. So that means I can write this as 2 square root of 5. So the square root of 5 plus 6 square root of 20 is equal to the square root of 5 plus 2 times 6 times the square root of 5, because I'm replacing 2 square root of 5 with the square root of 20. Now I'm just going to add or multiply 2 and 6, that's 12 square root of 5. Now I have the same radicand, the same root square, and I'm just going to add the coefficients. 1 plus 12 is 13 square root of 5. So that's the rule for adding and subtracting. We have to make sure that we have the same radicand and the same root. If I just the cube root of x and the square root of y, I can't add those. They're different roots, even though they're the same radicand. They're the same thing under the radical sign. Square root of x plus the cube root of x is equal to the square root of x plus the cube root of x. Can't add. This is a cube root. This is a square root. They have to be the same roots. All right, let's look at something useful. Let's call it rationalizing denominators. It's best to, let's look at an example and see what we're doing. So when we say we want to rationalize something, we have the square root of 5 divided by 2 times the square root of 10. So we want to rationalize means I want to get rid of this root in the denominator. I want this to have all of the roots radicals on top, and on the bottom, I just want a number. This should be easier for us to handle doing that. So how? How do we rationalize? When it's a single term, 2 times the square root of 10, we multiply by the square root of 10, the top and bottom. So this would be true if you have a single term you want to rationalize, you always multiply by the radical that's in the denominator. So we're going to multiply by the square root of 10. You might be asking yourself why, because this doesn't look easier. But let's look at the steps. I'm just going to write it using our rules. And you should see down here that I have 10 times 10, which means I can evaluate that as 10. Two numbers that multiply that give me 100 is 10 times 10. So I bring out a 10. This is 10 times 5. Well, 5 times 2 is 10, so I can write this like this. This is 10, 5 times 2. So what I have then is I have 5 times 5 times 2. I can bring out a 5, and the square root of 2 stays, and this is 10. Of course, we can simplify 5 over 10 is the same as 1/2. So this is the square root of 2 over 2. So why is this useful? I will say in most mathematics, it's easier to handle rationalized radicals than not, especially in calculus. Any computational mathematics, having the radical in the numerator is easier and more straightforward. I might be overstating that a bit, but I find in calculus that when I help students or with calculus and we have some function with radicals, in the numerator, you can write them as rational exponents, which we'll get to shortly, and it becomes easier to handle taking derivatives and looking at integrals and so on if you go that route. Otherwise, it's just prettier. I mean, honestly, square root of 5 divided by 2 times the square root of 10 is ugly. Square root of 2 divided by 2 is pretty, in my opinion. So let's look at some more. So I want to rationalize that. Now I just have a variable. I have y and x. The rule's the same. I'm going to multiply the top and bottom by the square root of y. This becomes 3 times the square root of x, y. Product. This is 4. Now I have y times y. Remember the rule, this becomes y. So this is 3xy divided by 4y. Now, it's not simpler. It doesn't look simpler, the two expressions here, but it is rationalized. So what do we do if we don't have a single term on the bottom? What if we have something more complex that's not just a single term? Let's say we have something that looks like this. 1 plus the square root of 5 in our denominator, 4 in our numerator. How do we rationalize? If we just multiply by the square root of 5, we won't have eliminated the radical in the denominator. If I multiply the denominator by the square root of 5, if I distribute this, I get the square root of 5 plus the square root of 5 times the square root of 5 is just 5. So you can see I still have a square root in the bottom. So that's not rationalized. So what do we do? Well, there's one of the prettier words in mathematics is we use the conjugate and multiply the top and bottom by it. So what is a conjugate? Well, I use the same expression. Let me rewrite this here. I'm going to put brackets. I'm going to multiply by the conjugate is the same expression, but I reverse the sign. Meaning I take, if it's an addition, I make it subtraction. If it's a subtraction, I make it addition. The reason is that when we multiply through, and I want to be careful. I keep doing that. it's not all under the radical. I'm just rewriting it. I'm actually doing anything to it. 1 minus the radical. Now this, and this is an upcoming lecture review. We would FOIL this. It's a form of distribution. We multiply the first terms, we multiply the outside terms, we multiply the inside terms, and we multiply the last terms. And doing so will get us a four terms, which the middle will drop. So if I did this literally, 1 times 1 is 1. 1 times the outside, -5, that gives me the square root of -5. -5 times 1 gives me the positive square root of 5. And then square root of 5 times square root of 5 gives me 5, but it's negative. So you can see that, again, we'll go over FOIL in future lectures. But for now, you can see that these middle terms drop, and I have 1 minus 5, which is -4. 4 divided by -4 is just -1. 1 minus the square root of 5, that's -1, plus the square root of 5, which, you want to be nice, it looks better this way. All right, so conjugate is useful. It helps us rationalize. Now this and this are the same expression. One is a little bit more clear. 4 divided by 1 plus the square root of 5, square root of 5 minus 1, I think is a little bit clearer. Next, let's go on to things other than the square root. So far, we've been dealing with the square roots. Remember, if there is no number there, we assume a 2. But we can have what's called the nth roots. And n could be any number, any integer. So n is an element of the integers, meaning n is 1, 2, 3, 4, and so on. And the reason we don't write the square root of 2 is it's most common. So other roots we write so we can differentiate. We call this the cube root. This we just call the fourth root. The fifth root, you guessed it, fifth root. So we always write the roots when it's not 2. So these work exactly the same as square roots in sense of how do we evaluate. So for example, if I have the cube root of 27, now I need 3 numbers that multiply together that give me 27 if I can evaluate. So 27 is 3 times 3 times 3. Since I have the cube root, I need 3 numbers that multiply that give me 27. So this evaluates to 3. Let's use something larger. Let's say the fifth root of 32. We need 5 numbers that multiply that give me 32. I'm picking nice numbers, by the way. It's 2 times 2 times 2 times 2 times 2. So if there's 5 of them, I could evaluate that as 2. Of course, your calculators will handle this, but this is what's happening. Again, we're taking out 5 numbers that multiply that give me the radicand. It helps when we're simplifying. So same principles apply. Let's look at another example. So we can add and subtract using the same property. The first thing I look at is if I want to subtract these, I need the same root. So we have the fourth root of 3 and the fourth root of 48. So the roots are the same, but I don't have the same radicand, do I? Well, let's look at what 48 can reduce to. If I want to put this in prime factorization, easiest if it's even, divide by 2. You can go straight to what you probably know it should be, but that is 2 times 12. This is 2 times 6. This is 2 times 3. So that means the fourth root of 48 can be written as the fourth root of 2 times 2 times 2 times 2 times 3. So 4 of these means I bring it out, and I'm left with the fourth root of 3. So that means the fourth root of 3 minus 2 times the fourth root of 3. Same roots, same radicand. I subtract the coefficients. 8 minus 2 is 6, the fourth root of 3. I would recommend writing your roots, if you're doing this by hand, as small as you can so you don't confuse yourself, that I'm not multiplying 6 and 4 at the end here. All right, so let's bring the last lecture and this lecture together by looking at what's called rational exponents. So what's a rational exponent? Well, it's a way to write a root. If I have the nth root of a raised to the power of m, I can write this as a raised to m divided by n. In other words, I take the root is the denominator, and the power of m is the numerator of a fraction. Let's look at an example real quick. So the cube root of x squared is x 2/3. The root is always the denominator. The power of the radicand is always the numerator. The square root of 7, we can also write as 7 to the 1/2. So this works both directions. I can always write a rational exponent as a root. So let's make a note real quick of a key fact here, and we'll explain why it's true. Now above, I said that this is the same as the nth root of a to the m. It also happens to be the same thing as the nth root of a quantity to the m. Now, why is that true? It's convenient. We're glad it's true, but why is it true? Let's look at an example. Let's say x to the 2/3. So I know I can write that as the cube root of x squared, which is the same as writing this as the cube root of x times x. The product rule says I can separate these. And then literally, this is the cube root of x times the cube root of x, which is the same as saying cube root of x squared. So these two things are exactly the same. It might not seem that way, but this is why. And sometimes it's much easier to write the external square than the internal square, depending on what it is you're trying to do or simplify. So let's look at a case where that might be true. Another example. Say we have 343 to the 2/3 power. And we want to know, what is this number? Is this a number that we could evaluate just off the top of my head? Looking at it, it's like, this is not pretty. Well, let's apply the rule. We know this is the cube root of 343 squared. Now, I don't want to square 343. That's 343 times 343. But I know I can write it this way. It's a cube root of 343 squared. Is that better? Well, let's break down 343. So it happens that it's 7 times 49, and 49 is 7 times 7. So I can write this as the cube root of 7 times 7 times 7 squared. Now, the cube root means I need 3 numbers and multiply. That means I bring out a 7. So 343 raised to the 2/3 power is actually the same as 49, which is nice. It's easier to do. You can put that in your calculator, you would get the same number. But if you had to do it by hand for whatever reason, on an exam, on a quiz, and homework, that's how you would do it. All right, so let's look at simplifying rational exponents. So we had a rule in lecture 3. And again, I said I wasn't going to do too much, but let me write this real quick. If I have two bases that are same, to raise to some power, I can write the power as an addition of powers. The same is true as if I have the same base, but with a fractional or rational exponents. This is the same as 1/2 plus 3/4. Now I need a common denominator, so I have 2/2 plus 2/4. I'm trying to erase, I swear. So that's 5/4. I can also write this as just the 4th root of x to the 5th if I wanted to. Notice that this would be x times the 5th root of x, because I have 5 of these, and the 4th root says I take out 1 for every 4 and leave the last. So yeah, that's that. If I have something like this, I'm going to write it like this again, x to the 5th. And I don't want to take the quantity, so let's just look at what this is. Remember, it's a 4th root, so I need 4 numbers that multiply that give me what I need. There's 4 here, so I bring one out, and I have the 4th root of x. All right. Another example, rational exponent, simplifying. I can write this as a square root, 9/16. The quotient says I can take the numerator and denominator. I know 9 is a perfect square, it's 3 squared. I know 16 is a perfect square, it's 4 squared. So that simplifies 9/16 to the 1/2 is the same as 3/4. All right, let's look at a complicated problem. And complicated, I just mean it just looks nasty. Hopefully I won't make too many mistakes. So 250x squared, the square root, divided by 100 b to the 3rd. My paper's flying. Let's say 7, the square root of b, divided by the square root of 125 x. So we're multiplying these. They're all square roots. So let's look at 250. Let's do some reductions here. That's 250 times 10. That's 5 times 5. This is 5 times 2. So the square root of 250 we can write as 5 times 5 times 5 times 2. Now it's a square root, so I just need 2 and bring out the 5, but then I have this left. So this actually simplifies to 5 square root of 10. And x squared, the square root of x squared is x. So 5x square root of 10 is the numerator. Now we know that 100 is a perfect square, so that means we're going to have 10, because 10 squared is 100. And b to the third square root is going to be b square root of b. Why is that? Because b times b times b gives me b to the third square root. I take out the pair. So that leaves me with 10b square root of b. Let's leave 7b alone here. Now, what about 125? Well, 125 is 5 times 25. It's 5 times 5. So 125 can be rewritten as 5 times 5 times 5. Square root means I take out for every 2. So then I get 5 square root of 5. And I have this x here. All right. So I wrote a lot. So let me move this down here. 5x square root of 10 divided by 10b square root of b times 7 square root of b, 5 square root of 5x. All right. So I notice here that I have a 7 square root of b. I'm going to divide that by 10b square root of b. And I'm going to put the 5x square root of 10 divided by 5 square root of 5x. Again, these are properties of real numbers in lecture 2, I believe. If you need a refresher of why I can move stuff around that way. So the square root of b divided by the square root of b conforms to our rule that if I take 1/2 and b 1/2, I'm converting them to rational exponents. The law of exponents says that if I have a quotient, that I subtract the power of the numerator from the power of the denominator. This becomes b to the 0, and anything to the 0 is 1. It's a fancy way to say that b's cancel. So this becomes 7, 10b. Now we have a 5 here, so 5 and 5 cancel. Then we have x square root of 10 over 5x. So let's put all this stuff together. 7x square root of 10 divided by 10b square root of 5x. We could stop there, or we notice that we have a radical in the denominator, and we've been told we don't like those things. So let's multiply it by 5x square root top and bottom. This gives us 7x 10 times 5x by the product rule. This gives us 10b. Now 5x square root will give us 25x squared, which is 5x. So this becomes 7x square root of 50x divided by 50 bx. So we're using a lot of rules. We're using a lot of the properties of real numbers. Notice here that we can cancel this x. So we have 7 square root of 50x divided by 50b. Now what about 50? Can we reduce 50? Well, it's 25 times 2, 5 times 5. So that is 50 square root is going to be 5 times 5 times 2, which is going to be 5 square root of 2. And we have to leave the x, so this becomes 7 times 5 2x divided by 50b. Now this 5 goes away, this becomes 10, so we have 7/10 2xb. So 7 times the square root of 2x over 10b. Did that quick? Check me out. Let me know in the comments if I made a mistake. It's possible I go quick. But that's pretty much all we wanted to talk about for this lecture. So that's radicals and rational exponents. The next lecture will be on polynomials. If I could spell it. So we start getting ever closer towards the beginning of the college algebra course. Polynomials are the heart of college algebra. So we will take a look at those next time. Thanks for watching. Like and subscribe if you can. It helps me out. And I hope you have a nice night.